In this video, I'll explain how to make the TFT screen-based Spatial Light Modulator, or SLM. This allows for programmable and dynamic Fourier light filtration to implement advanced contrast methods. You can implement some advanced contrast methods without this SLM, using PUMA's easy-to-access Fourier plane of the condenser with a simple filter system. This filter tray can take a standard 25mm round glass cover slip on which you can print any arbitrary aperture in black and white or various colors. So, you don't need this TFT SLM for doing things like Reinberg filters, oblique illumination, Schlieren phase contrast, dark ground illumination, and other static custom apertures. The real benefit of this TFT-based SLM is its dynamic, programmable nature, which allows you to derive optimum apertures algorithmically and to perform aperture scanning, such as for Fourier ptychography and 3D tomography. It also allows you to change apertures rapidly during observation without mechanically disturbing the microscope by physically changing the filter in the slot. In general, a spatial light modulator refers to any device that can alter the characteristics of a field of light in a way that varies from one part of the field to another. This spatial pattern of variation may be static or it may be dynamic, for example by being under computer programmable control. Examples of characteristics of light that an SLM can modulate include its amplitude, its phase, and/or its polarization. So, an amplitude SLM, for example, alters the amplitude or intensity of light coming from it in a way that can change at various points across its surface. SLM devices can be reflective, such as a digital micromirror device or DMD, emissive, such as an LED illumination matrix, or transmissive, such as a transparent TFT display device. The PUMA SLM is most often used as a transmissive amplitude SLM, which uses the polarizing effects of a TFT screen to restrict the passage of light through it at any point across its surface in a way that can be controlled by a computer. However, if you remove the upper polarizer filter from the TFT, then it becomes a polarisation SLM instead. Before I move on to the next part of this video, I would ask that if you like these PUMA videos, please take a second to support the project by clicking on the big red subscribe button and give the video a thumbs up. If you have social media accounts, also please share these videos on them using the YouTube share button. Okay, now back to the rest of this video. The PUMA SLM is a color SLM in that it can restrict light passing through tiny RGB filters differentially at each pixel position, and it can restrict the light in a graded way, so not restricted to all or nothing passage like a traditional physical aperture. Because the PUMA SLM is based on a TFT screen, the light passing through it will be linearly polarized. This may be an advantage, a limitation, or a neutral point depending on your intended application. Unlike an emissive LED array, the PUMA SLM has a higher spatial resolution of more than 45,000 addressable pixel positions across its 24mm clear round aperture, compared to less than 1,000 for LED arrays that have been used in the published scientific literature to date. Also, the amount of light transmitted by a PUMA SLM is limited by whatever illumination source you choose to use, including laser light, whereas LED arrays are limited by whatever output each LED can produce. The PUMA SLM is also much cheaper than other SLM types, being based on this inexpensive TFT screen module costing only a few pounds, whereas a typical DMD costs over £100 and a phase SLM can cost over £10,000. There are, of course, some limitations to the PUMA SLM. Firstly, it cannot produce 100% blockage of light. Even the black areas allow some light to get through. The stated contrast ratio for the TFT is about 800 to 1 according to the product datasheet. However, in some circumstances, this light leakage can be used to advantage. Also, the PUMA SLM is not completely optically clear. It has some diffusing properties. For this reason, it cannot be used behind the objective lens, for example, to effect Fourier filtration in the back focal plane of the objective. And, when used in the lower focal plane of the condenser, it will blur the image of the field stop, so will not permit full color illumination. This latter issue is not practically important in most cases, because the field stop image is not as important in reducing internal reflections in a PUMA scope as it is in some other and older microscopes. It is possible to remove the diffusing polarizer film on the front of the TFT panel and replace it with a clear non-diffusing film. However, that will not solve the issue because the interfaces between the RGB filters for the pixels in the glass of the TFT panel act as a kind of diffraction grating and so can cause some dispersion of the transmitted light anyway. The diffusing polarizer actually helps by eliminating these diffraction grating effects, so I do not recommend replacing it. Finally, it's quite difficult and potentially dangerous to remove the backlight from one of these TFT displays, so it's difficult to make a PUMA SLM, whereas other types can simply be bought ready to use. Be warned that there is potential risk to your eyes from shattering the thin glass in these displays while attempting to remove the backlight, so you must always wear laboratory-grade eye protection if you attempt to perform this procedure. For the same reason, do not perform this procedure in the presence of others unless they too are wearing appropriate safety goggles, and do not attempt this procedure in the presence of any pets, food or drink that could get contaminated by flying shards of glass. Take appropriate precautions to prevent cuts to yourself and others from handling the sharp tools used in this procedure as well as from potential glass fragments. Take care to clean the work area well afterwards. There is also a high risk that you will permanently damage or destroy the functionality of the display at any stage during this procedure, so do not attempt this procedure unless you're prepared to accept such loss. The method I'm about to show you is not foolproof and does not guarantee success. These are the parts and the tools you'll need to build the SLM. Details are provided in the video description. First, clean up the printed parts and test the SLM holder to see if it fits easily and with minimum force into the slots you intend to use it with. Here I'm using an Abe condenser. Ensure that the adapter module is attached to the condenser during the test, either the condenser to mirror holder adapter or the condenser to upper collector adapter. If there is difficulty inserting or removing the SLM holder, scrape and/or do whatever else it takes to fix the problem at this stage before inserting the delicate TFT screen. Ensure that the slot that will accept the TFT panel is clear of any stray plastic blebs or threads. Before modifying the TFT screen, first connect it up to a suitable power supply and display driver and test it. Here I'm using the PUMA Control Console or PCC, but you can use your own custom driver. This is so you know that the screen is working and undamaged prior to modification. You should also test the screen at various stages of the procedure to ensure it still works, but make sure you do not perform any aspect of the procedure with the screen still powered on, or you may short-circuit the electronics and destroy the screen that way. Now solder the connector to the screen. I use a 7-pin JST-XH male PCB header with 90-degree pins as shown, rather than the supplied connector, because it ensures I connect the ribbon cable the correct way round each time, provided of course you connect the header the right way round at this stage, so ensure you connect it as shown. After soldering, test the screen to ensure it still works. The next step is to reinforce the very fragile thin glass connector strip with some strong epoxy resin and allow it to set fully before continuing. This will increase your chances of success, but it will not fully protect the thin glass from cracks, so you must still be very careful. When you do this, ensure that the epoxy does not go right to the edges to contact the metal or overflow down the sides to the underlying layers, and minimize any overspill onto the top of the screen. Carefully, gently and slowly lever the TFT screen metal housing case off the PCB with a broad flat blade. It is held there by adhesive glue or foam. Once it is free, test the TFT again to ensure this hasn't broken it. Carefully, gently and slowly use a fine-toothed craft saw to make score marks on the PCB on the two sides of the slot that the TFT screen ribbon cable passes through. The side that has the greatest clearance from the ribbon cable is scored horizontally until all the copper layer on both sides has been cut through, and some of the PCB substrate material as well. On the opposite side, you're too close to the delicate ribbon cable to score parallel to the PCB's surfaces, so score it on its edge, taking care not to stress the cable by putting pressure on the free TFT metal enclosure. Once scored on both sides, use long-nosed pliers to rock back and forth the outer strip of PCB till it snaps off. I snap off the end that was scored horizontally first, and then the end closest to the ribbon cable. Test the TFT after this to ensure it still works. This is all tricky and delicate work, but now comes the most delicate of all, removing the metal casing, reflective panels and backlight LEDs. The ribbon cable is connected to a very thin extension of glass coming off the bottom of the main glass panel. We partially reinforced this earlier with epoxy, but it is still very easy to crack with only minimal pressure. With this in mind, wear your eye protection goggles and do the following. Carefully, gently and slowly use a scalpel to get between the metal and the glass panel. Push the blade right down vertically till you reach the bottom of the metal casing, and then slowly bend the scalpel blade away from the glass to open up the metal casing's side panels. Avoid doing this at the bottom where the thin glass extension is, but do it everywhere else. Carefully, gently and slowly use the scalpel to lever the TFT plate out partially from the top and side. Don't lever it out fully or all at once, otherwise there will be pressure at the join of the main glass panel and the fragile connector extension glass, and it will crack. Carefully remove the mirror and layers of the diffuser, being very careful about not putting excess pressure near the base where the thin glass connector is. Carefully, gently and slowly use the scalpel to remove the glue from around the periphery of the main glass TFT panel. Carefully, gently and slowly use the scalpel to release the LED panel from the bottom. Use extreme caution when doing this because you are near the fragile thin glass and fragile ribbon cable. The LED panel has its own little separate ribbon cable for power. Test the TFT panel again at this stage. If all is working, disconnect the power supply to the screen and cut the LED cable with sharp scissors, taking care not to damage the main TFT ribbon cable. Test the TFT again to ensure it still works. Fit the TFT panel into the IAD SLM 3D printed parts as shown. Be very gentle not to use force, or you will break the thin glass connector or slip and rip the delicate connector ribbon. The screen has to be placed the correct way up because these components on the PCB need to fit into this hole for them in the handle area. Secure the handle cover on the IAD SLM with the 4 M2 screws and nuts as shown. Note that the handle and cover are not symmetrical. You must sight the cover as shown with the PUMA SLM label facing out and the letters the right way up if you hold the filter with the handle pointing down and the TFT screen aperture pointing up as shown. Test the resulting IAD SLM TFT to ensure it still works. Now that it is fully assembled and working, disconnect the power and further strengthen the fragile thin glass connector by putting a second wave of epoxy in the recess around and over the thin glass extension to strengthen it. This time you must glue right to and over the sides of the glass screen and contact the plastic of the handle with the glue to prevent the TFT screen from slipping during use. Just be careful not to get any glue on the clear aperture and avoid going over the top surface of the filter slider itself. After the epoxy has fully set, test the unit for the last time. If it works, then you have succeeded in making your fully functional PUMA SLM module. Always take care when inserting or removing the SLM from a filter slot not to put bending pressure between the filter handle and the filter slider. I tend to hold the SLM by the sides of the slider, not the handle, when inserting it most of the way, and only use the handle to push it in the final amount till it clicks in place. If you feel undue resistance, stop and investigate why. Never force it in. When removing the SLM from a slot, I usually push the SLM from behind as shown, rather than pulling it out via its handle, because pushing it out in this way results in less chance of accidentally putting bending pressure on the thin glass connector plate. In other tutorials, I'll show you how to use the SLM to achieve advanced contrast modes of imaging. This video has been primarily about the mechanics of building and using the SLM. Thanks for watching.